already taken a session on machine learning, and he'll take you a step further.
Is it audible? So, check the shocks. So this is the title of the talk, from mathematics to machine learning. In last 2 days you might have gone through a lot of maths courses like linear algebra, probability, optimization. So we'll see how these things actually play a very crucial role in designing solution for machine learning problems. In the first talk on machine learning, we have seen several prediction problems, right? Mostly machine learning deals with analyzing data and predicting some trend for the data. So to give you some examples, let's say you have a set of examples that these emails are spam and these emails are non-spam. Now if you give a new email to a computer system, whether it will be detected as spam or non-spam, how to design that kind of rule or algorithm, that's what is machine learning all about. It can be used for predicting not only like things which are for one class or other class. It can be used to predict something like given the temperature of several other days, can you predict the temperature for tomorrow or day after tomorrow. So in machine learning, we classify these kind of problems into two categories. What is supervised learning? Does anybody know? So basically, if I give you the input as well as the output, several of them, and then I give you a new input, whether you will be exactly able to predict the output or not. So that kind of problems are categories in terms of supervised learning, where you already know some pairs that for this particular input this is the output. Like for a image classifier, which basically given an image, let's say whether this image contains a car or a bike, for example. So you will be first given a set of images which has a bike. You will be given some images which will have car. So you know that this kind of image which has car looks like or something like, you have some kind of characteristic of those images which has car or which has bike. So another image when you will see, you can relate it to the things that are given. Like you can see that whether this is similar to the one which contains bike or this is similar to the ones which contain car. So then you can take a decision, this is more similar to the one which looks like a car. So this is called example based learning, and we call in machine learning terms supervised learning, because you know beforehand that things look like this. Now there are two categories. One is classification and another is regression. In classification, you have to say whether it belongs to class 1, class 2, or there can be n number of classes. For image classification, it can be car or bike 1 or 2. It can be spam or non-spam. In some cases, you might be having more classes if the images have several other possible alternatives. So there are finitely many. In regression, it will be like predicting a real number, similar to what will be the temperature tomorrow, or how much rainfall is expected. So you have to just predict a number. So in this talk, we will see how to design this kind of classification, how to design a solution for classification problem as well as for regression problem. We will take clues from mathematics. That's the idea. So to start with, let's say x denotes input and y denotes output. And I tell you the value of x is 2, and then it gives value of y as 4. Then if I ask you to predict what is the value corresponding to x equal to 3, can you guess anything? Okay, let me get the answer. So 1 is 9. Any other? 6. 5. So now let me ask you, what rule did you apply to get this answer? So might be you apply here y equal to x square. So this might be a rule like y equal to 2x. Right? 5, who answered 5? Yeah. So now you have several choices. Which one will you pick? Do you have any idea? Really, you don't know. Now let's say if I give you another choice, let's say here corresponding x equal to 5, I get, let's say 7. Then you know that out of all these 3, this is giving you better on this also, right? Based on the first, you came up with all these alternatives. Now I told you that for x equal to 5, you get y equal to 7. Now you, let's say you evaluate this one. So in this case, y should be 49, right? But you, not 49, 25, right? 25. But here answer is given 7, so it doesn't match much. Same thing here, it is 10, here it is 7. This case 7, it exactly matches. Okay. So one thing is important. So that once you have data, more data, you can learn the exact underlying model, which is giving rise to those outputs. But if you have less number of data, if I only told you x equal to 2 gives y equal to 4, you might not have any clue that what was the correct answer for x equal to 3, right? The moment I told you that it gives 7 for x equal to 5, you know that if the underlying thing was a linear one, this one, then this is the correct one. But consider this situation now. So here I am plotting x corresponding y. So x equal to 2 gives y equal to 4. So this is the point. And then x equal to 5 gives something like 7. So you try drawing a line. Now if I tell you any other x, you can easily predict the y. But suppose someone chose this kind of model. Let's say I chose a function which is like a parabola. Consider this case. So y equal to x square may not be valid, but I can always find a parabola passing through these 2 points, right? So now somebody might say for x equal to 3, this is the answer, instead of saying this. So how do you know whether this is the correct one or this is the correct one? Because we don't know. So another thing, what is important is, let me write it. So straight line means you have 2 parameters, a and b you don't know. If you have a parabola, it will be something like ax square plus bx plus c, right? You have 3 parameters which you don't know. The idea is, the more you have data, you can get clue about these parameters. But if you have less data, you will not be able to know what are the exact values of this. In this case, see, if you choose this model, you know what all A and B are, right? But in this case, can you say what are the values of A, B and C? Is it possible to tell from these 2 points? Okay, so we'll come to this problem in a minute. So now consider these 2 problems, and I denote this input and output as, for x1 corresponding output is y1, for x2 corresponding output is y2, like this. Okay, so if I am given on n instance of such things, xn, yn, and then I will be asked for x, what is the output, for corresponding x, what is the output, I will be asked. So this is the kind of setting we are talking about in machine learning. You know the corresponding these x's, these are the y's, and finally you have to predict y for unknown x's. So it involves 2 things. One was the model that you take, whether you want to only fit a line, whether you want to fit a parabola, or you want to fit something else. That is called model selection problem. Now once you select a model, let's say you select this one, I want to fit only lines. So what you will do, let's say I have to write y1 as ax1 plus b, y2 equal to ax2 plus b, like this. So this will become a system of linear equations. N variables are there, not n variables, 2 variables are there, and n equations are there. You can write it in matrix terms. A1 to an, this side will be x1 to xn, this will be y1 to yn. In matrix notation, this is what it looks like. If you are given all these y1 to yn, x1 to xn, you will be able to solve a and b provided there are certain conditions. Can anybody tell what are the conditions under which you can solve this thing? Very easy. So you will be given n points, right? N points can be anything, right? And what we are doing is we are finding a line which satisfies all of them. It is not always possible, right? If there are 2, it is easy to draw, but if there are n, where n is more than 2, it is not always possible to draw a line which passes through all of them. So in case all of them lie on a line, it will be possible. If it is not, then there is no way you can get it. So this equality may not hold always. And from linear algebra, what it says is your dimension of this dimension is 1 cross n, right? So what is the rank of this matrix? One. It can be at most 1. So in case there is no, if it is all zeros, then it will be 0. If it has a non-zero entry, then it is 1 basically. So the rank 1 matrix, but here you have n generally. I'll write here. What I'll say, this is, let's say generally you have seen equations like this, ax equal to b, right? Where you write x equal to a inverse b, right? So here what you see generally, this will be a square matrix, and you compute its determinant, it should be non-zero, so that you can invert the matrix and get the solution, right? And here we don't have a square matrix, okay? We don't have a square matrix, but you want something like, if I have to invert it, so x1, I wrote something, okay, let me clearly write this. It should look like x1 to xn, a, b, so this is the matrix form. I think what was written was wrong. So this is correct, right? No, this is still not correct. So it will be x1, x2, xn. This side will be 1, 1, 1. Is it correct now? Okay. So basically you have something like this, right? Here is the A matrix. Here you have a something unknowns, and here this side y you know. You have to find x or the parameters a and b by inverting this matrix. But in general, this matrix is n cross 2, so you cannot invert. So there is a solution for this kind of problems also in linear algebra, where you have this kind of setting where you may not have a and b possible which satisfy all of them. So in that case, some other solution. You might have a and b possible, but there are infinitely many possibilities, out of which one you should pick. And the best case is where you have a square matrix, you can just invert, you have only one solution. So, but in machine learning, what are these things? I'll denote it n is the number of examples given. So that I'll say number of examples. I'll say M is dimension of data. Dimension of feature vector. What is feature vector? So corresponding to x1, my feature vector phi of x1 is basically 1 and x1, a vector basically. You have seen in most of the machine learning problems, you will be given images, you will be given documents, news articles, or maybe some reviews written about something. So all we will convert it into vectors, which is like a tuple of numbers. So in this case, given the x1 will form a vector 1 and x1. So that is my feature vector. Those are called feature vectors. And here m is the dimension of a feature vector. In this case, it is m equal to 2, right? There are two components. So the thing is, m is 2 here, and n we are considering here, let's say much greater than 2. You will be given so many examples so that you know better that whether it is parabola or whether it is line or something else. In this case, if I give you only 2 data, you don't know whether it will be line or parabola. But if I give you more data, if data looks like this, okay, so you can assume that more or less this goes in a straight line, or in case data goes something like this, so you know that something like this. So more data means you have better idea about which model to fit. But the problem will be generally, see, we are all plotting in 2 dimension. Let's say you are given a document. What will be the vectorial representation of the document? X is what all words are there, okay, and corresponding to each word, how many times those words have appeared in that document. So if you have a dictionary of 60,000 words, so corresponding to each word, it will denote the count how many times those words have appeared in the document. So it will be a very big vector of 60,000 dimension, and it will not be possible for you to visualize that, and you don't know whether linear will fit or the parabolic will fit. So that's where the computational challenge comes, and computer science gets involved in this. So in this particular problem, we have m is 2 and n greater more than 2. So your problem will be to solve given the, okay, so this I will denote this as one problem, and second is the document thing that I told, where you will have the m as, let's say, 60,000, okay, and n will be, let's say, you will be given some 1,000 documents. Here also consider you will be given some 1,000, let's say. So there are two scenarios where your dimension is less and where your dimension is more. Now I relate it to this problem actually. Here you have a system of linear equations which comes from this kind of setting actually, and you have two parameters here. The matrix is n cross m, right? N rows and n columns, and there are two possibilities where n is more or m is more. What happens when you have now n is more than m? That means I have less number of variables. I have only two variables. I have n data points, right? In that case, what happens? I showed you that I have more data points. I am fitting in 2 dimension, and it may not always be possible to draw a line. So you may not find the exact solution. So you have to find some approximate ones. So that is the case here. Some approximate solution you have to find. M greater than n, where you have more parameters and you have the number of equations are less. So you can always, just like if I give you only one point, you can fit many lines, right? Many lines passes through it. So where number of data points are less and the parameters are more, you will have many solutions. Now both cases you have problem. If you have to approximate the solution, what will be a good approximation? And in case there are many solutions, which one shall we pick? So two problems arise in machine learning. Now let's see how we can solve those problems. So one thing is, let's say if I give you let's say I want to learn this model. I want to fit a line, but no line fits exactly. I want to find approximate ones which fits the given y1 x1 pairs. So what I will be doing is, I will take this function, I will compute what is called y1 cap. What is that? I will put x1 for some a and b and find what is the y1 cap. But I know that y1 is something else. So I will know what is the difference, y1 minus y1 cap. So this is the error I incur, right? If I given x equal to 2, I predict, let's say 3.9 instead of 4, x equal to y is 4, but my ax plus b says it's 3.9, I incur loss of 0.1. Yeah.
What's m, sir?
M is the dimension of feature vectors. So in document, like in this case, see this matrix has a number of rows as n and number of columns as m. So m is the dimension of the feature vector. So in this case, what I am using is, see, to predict y I am using x and b times 1, right? So my values are this x and 1 are my feature basically. So in case of a document classification, I told that word counts. So you have 60,000 words corresponding to each word, it will have a count. So you will have a big vector. Instead of 1 and x, you will have so many components. Any other doubt?
That ax plus b is because you are trying to express it in the form of line.
Yes. So basically, first thing we told that machine learning one problem is the selection of model. Whether I want to fit a model or I want to fit a parabola or something else, so that is called model selection problem. Now once I believe that line can do a better job, I don't need to go to parabola or something higher order. So we fix the linear one. Now out of line, which one will be good? We don't know, right? So based on those x1, y1 that are given to you, you have to find which a and b will be best for you. And I told you, if you have a square matrix, then you can easily invert and get the answer. But in general, you will have only two kinds of situation where either you have more number of data points or you have a very large number of features. So in both cases, you have problem. One is the approximation problem, another is the you have many solutions which one to pick. Right? Many solutions. Did you understand what is the exactly problem? The moment I told you x equal to 2, you tried giving so many answers. Why? Because there are many solutions. So that is also a problem sometimes. It is not that exactly if you want to predict. So you said y equal to x plus 2 and y equal to 2x. Both gives this one, right? X equal to 2 if you put, both gives y equal to 4. But for x equal to 3, both will give different results. You don't know which one to pick. Literally both are good. As long as you know that x equal to 2 gives y equal to 4, both looks good, right? You don't have any other criteria to judge which one will be the better one for predicting the future. So in this case, which solution to pick? So that is also a valid problem. So now consider these two cases where m is less and n is large, and in this case m is large and n is less. The first one. So I designed a prediction rule that I will be using A and B to predict the y. Okay, this is the rule. Any x you give, I will give you a y. Now let's say you put x equal to 2, not x equal to. So you put x1, you will get a, the system will give you a y1. It may not be exactly the same as the one that was given corresponding to x1. So you have corresponding value as y1, but the system gives you a x1 plus b, right? So it may not always exactly be fitting y1. So what you will do is, if y1 is the correct answer and your system is given a x1 plus b, so this difference I want to minimize basically. So let's say I take a square. So if the value is 0, then I know y1 is equal to x1 plus b. If it is small, I know the error is small. If the the quantity is large, then no, my model is not doing a good job, right? So this captures the notion of how good the predictor ax plus b working. Is it okay? What I am saying, you choose. So this was the problem given, right? Y equal to 4. Now you choose some a and b, right? And then you start predicting y. Okay. Let's say you choose some a equal to 3 and b equal to b equal to 0. Let's say. So it is basically y equal to 3x. So your y kept giving 3 times 2 6. But your answer is 4. So it is not close. So you have to tune this a and b so that it comes close. So generally in machine learning we pose these problems as, for yi, the corresponding output system is giving xi plus b, and then we sum all such errors y equal to 1 to n, and then say we minimize over all possible a and b so that this quantity, my mismatch is less. Is the idea clear? Why am I doing this thing?
So like we are it is a trial or error method, like we are just deciding some value of a, b and then checking it whether
it fits.
Or not.
Yeah. So basically how we will be doing that? So what I am saying, if let's say you give me some a and b, okay. Now I will compute xi plus b for all such I equal to 1 to n, and then I will match with yi. If it matches, then it's well and good. If it doesn't match, I know that how much the mismatch is. The more the mismatch, I know that your predictor function is not so good. So given all possible choice of a and b, I will pick the one which gives me this error, the minimal, right?
So like it is feasible to have an error in trial method, like
No,
now
no.
you have only two.
See, we are not, first of all, we are not trying out A and B. What I am asking, if I give you, let's say, two sets of value, I give you A equal to 3, B equal to 0, and I give you A equal to 2 and B equal to 0. Which one will you pick? Which gives the less, right? The criteria I am asking. So, the criteria is which will give you less. The fit, this is called fit to training data. Because I want to exactly get as close to the points, the line should pass through. In ideal case, the line should pass through all the points, but if it is not possible, it should go close by. So that's the idea. It's called fit to training data. So now how to find this A and B? It is not a trial and error method. What we have studied in optimization, how to solve this kind of problem. This is a minimization problem. So one solution is, generally what it happens is, you start with some A0, B0. You start with some random guess, maybe 1, 1 or 0, 0 something. And you plug in those things, okay. You see the error, right? And based on that, you modify your A and B so that your AB classifier or AB fits this data better actually. So in one shot you will not be able to do, so that trial and error guess will go in a number of steps. So how to do that? It comes from optimization. So I'll give you one particular algorithm to learn this thing. So that is called stochastic gradient descent. So you start with some initial guess A and B, right? Some A0, B0 I am calling initial, that's why the notation is 0. Now first point you see x1 and y1, okay. What is the error? Error is y1 minus, you have used A0 times x1 plus B0, right? Whatever values you chose initially, you use those things to predict this, and you got some error. And based on error, now you want to take a decision, you want to change A and B. So what will be this change? It will be n0 plus something, you will add some, let's call it alpha times x1 times this, let's call it E1, error on the first example. If I update it like this, I just add some values like this. X1 and 1. Let me call it like this. It's let's see how this thing works out. So now if you again compute A x1 plus B, how much it will be? What it was like A0 x1 plus B0 x1 B0 plus it will be, see I'm putting these new values, so this is basically your A0 plus alpha E1 x1 and this is B0 plus E1, right? So this is the new A and B I will find. So here alpha is some parameter and E1 is the error I incurred. So this will be in such a way so that x1, so it will be alpha E1 x1 square correct, A0 x1 what did I call it, say, let's say B0 plus alpha. Alpha. So basically what I predicted last time plus some quantity which is proportional to the error I made. So this quantity is E1 times something, E1 times something. So what basically I want to say, you want to, add such that the amount of error that you make, based on that you change your values of the parameters so that it does better. So in this case, if you see that this was doing, so this is proportional to the error E1, right? Now if you subtract the error, right? It was Y1 minus something. So this will be like, this will be becomes 1 minus something. So let us do that part clearly, what we are exactly doing. Minimize, you had a function on A and B and you are minimizing over A and B. You started with some A0, B0. Then for t equal to 1, 2, let's say t rounds, what you are doing, AT and BT. In the tth round, how you are updating is, you are taking at the t minus 1th round, whatever it was, and minus some alpha times I'll say del f of del A and del f of del B. Computed at the last one. In optimization, you are going through gradient descent, right? No? So what you start with some initial guess, you know how to compute the derivative of this function with respect to A and B, and then in the current one, whatever derivative you compute, the next one you update, just the current update minus alpha times something. So if you keep on iterating like this, you will finally come to, after let's say 1000 rounds, you will come to a decent value which actually gives you a good fit. That's the idea of this kind of iterative algorithm. And what is the advantage compared to the the matrix inversion is generally in given a large matrix, let's say 10 power 6 cross 10 power 6, it may not be always feasible to load everything into a RAM and then do the computation. That is computationally the bottleneck. You cannot have so much of storage, and in iterative setting what you have to just load is just the n values, right? You have just the parameter and each time you have to just do order of n computation instead of the order of n square memory requirement that you had earlier. So this is why we generally all optimization algorithms, you may not see one shot solution like A inverse B, but you will start with some solution, and as you progress you will find better and better solution which actually computationally is feasible. You cannot process the whole thing together. So what we learned is, given a model like the line that we were fitting earlier and some training data, we have to come up with some goal, like minimize the the error in prediction or something like that, which gives rise to some minimization algorithm which leads to the the prediction rule, what will be the best choice of A and B. That's what, there will be many such algorithms for solving those things. But what differs is the criteria that you put. Whether you want to put, we put the criteria like, if you predict AXY plus B and your original value was YI, we predicted some square of this thing, right? Why not, if I can take YI minus AXI, just absolute value, right? This is also error, how much it differs, and just sum it up and process. So based on different criteria, you will have different kind of algorithms, but finally the goal is to minimize that minimize that objective, that you want to have less prediction errors. Okay. Now we started with line, but what happens if the original thing was really a parabola? How will you deal with that kind of thing? You don't have any idea about which model to choose initially, right? So we just started with a line. Now I'll show you how you can, instead of a line, the same line thing, the idea about fitting a line will just extend to anything, any polynomial or in general any nonlinear thing. So let's say, given x1, I consider phi of x1 as 1 x1 x1 square. Okay. I predict y cap as, I find 3 parameters a, b and c, right? It's also linear, right? Do you see how it is linear? Because it is also a, b, c is a vector and dot product between x1 square, x1 and 1. While linear means it should be dot product between the feature vector. So x1, for x1 I computed already 1 x1 x1 square, so this is a vector and ABC is a vector. I have to just dot product and then I get the prediction. It is same as the case that I had earlier, x equal to b. So in that case it was AB dot product with x and 1. So this is what the idea of feature vector comes. You might be given an image which has only the pixel values. So pixel values, let's say you have 10 cross 10 image, so you have 1 to 100 pixel values. Now corresponding, you might want to use only the pixel values, you might want to use the square, any power or something like that. There is no clearly defined rule that you have to use only the this 100 values. So that's what the feature transformation comes. I might want to fit a parabola. In that case, I want to choose x1 and x1 square, all those things. So in this case, can you say what will be the dimension? If I have 1 to 100 value, so if I want to use the values as well as their square values, how many it will be? 100 plus another 100 for their corresponding square. If I have to take like this first pixel and second pixel multiply together, so that kind of combinations I can take. So basically you can have anything represented in this fashion. You can have 1 x1 x square, anything. So what you see is the problem, this will grow, right? If this grows, this side also will go, right? So number of parameters more. So number of parameters more means another problem is this one, right? More parameters means you don't know many solutions. What will happen, you don't know. So in that case, you have to pick one of them which performs well, in the hindsight. You don't know which will be performing well, but you have to do a cautious choice. So that paradigms give you rise to so let me write. So you have a model, whatever it is. Let me first write xi plus b only. It can be generalized to any number so that you understand. So let me write this kind of thing only. So this final one goal is to either have this minimum, right? It has to fit well. In case there are many solutions, this will be 0 for many possible choice of AB. But on top of that, I have to show that AB is not too bad because there are many choices. So one particular thing that is used is you use something called let's say a square plus b square. This value should not be too large. Not too large. In practice, it has, it was, shown through experiment that if you choose not too large value, then your, the one A and B that you choose will be good enough for prediction. So what we do generally is we put a lambda. So lambda is just a positive parameter. So you don't want this much also to be too large. And this also you want as minimum as possible, because the predictions you want to match more or less exactly. So you have to do a balancing between these two terms. Your AB should not be too large, and your the model that you are fitting should go through the training data. So in this parameter is called regularization parameter. In most of the machine learning software that you will be using, you will be having this pre-parameter, and they will not tell you how to choose this parameter, because it's basically a trade-off. You choose linear model and then see this how it is fitting, and how the AB values, moderate values or large values, whichever is giving good result. So based on your trial and error, you have to find lambda. So this is because you have many solutions, but you don't know which one to pick, right? Do you understand the importance of this parameter? So I gave you two points I gave you. I want a predictor. So you can just draw a line. You can just draw this kind of curve. You can draw a parabola, anything, right? But which one to pick? You have too many choices. And so we want something which gives more or less, good results, as well as it should predict this, whatever, let's say if 2 are given, that is, it should predict both the points correctly, first criteria. So this will take care of that whatever points you are given, the curve should pass through, or at least pass close by to those points. Second terms, you know that in case there are many choices, which one to pick. Now, if the original answer was this and you picked this one, you will do really bad here, right? For this one, you will be predicting this, whereas the original is this. How to, stop those things from happening is through some kind of regularization function. So one kind of regularization function is this: the parameters that A and B are actually not too large. How it will play in the large case is M is 60,000. Consider you have 60,000 such parameters, A, B, C, D. So 60,000. So it is possible it can be any curve. But if all the coefficients are small enough, there will not be much variation. So that is the idea actually. So and how it is chosen, I will tell you the trick. So you will be given this n points. And apart from that, you will from n points, what you will do, you will keep some points separate. Let's say 10 points you keep separate. You only fit the n minus 10 points for a particular lambda. So you will get some A and B values. Now with those A and B values, you predict what is the result for the 10 that you didn't use, and see whether for those 10 it is matching or not. See, if it is matching quite well, you know that the lambda that I have chosen is okay, reasonable. If you choose lambda such a way that for those 10 points, whatever result it gives is not doing a good one, so you will reject that. So this is why it becomes trial and error, and it's in machine learning literature it is called cross validation. And as of now, this is the most popular technique to choose the lambda. There is no other way. You have to first choose a lambda and see how things working here, and then test it on those extra points, see if things working. If it doesn't work, you change the lambda, and like that it works. Because if you have used all the points, maybe it is passing through both the things, but you don't know what is happening to the unknown points. So to have certain control on the the prediction function, that it should not be too much 2 points, it can be anything, right? It can be like this also. But this may not be a good one to pick, but rather simple ones are better. So some choice is made here so that the prediction errors are not too bad. So what we have learned now is, given a problem, we have some training data, we'll keep certain percentage of it separate and fit a model It can be linear one, or it can be any polynomial, anything like that. So I can choose 1x1 or 1x1, x1 square, x2 square, anything. So once the model is fixed, I know I want to minimize the error. So this is the error term, and I'll choose something which controls my variability of the model. So I'll choose something like a square plus b square, or if you have 1000 parameters, so all the squared terms, and then I choose some weight so that both sides are balanced, and then I'll find the best possible a and b using the earlier technique. I start with some a and b, I use the gradient, I update and go on for some rounds. I get the best possible value of a and b. I test the other data which I didn't use here. I'll see how the lambda is performing. If it is not performing well, I change the lambda, I do it again. So that's how you come up with a model.
So can you please explain why you have used that lambda? Because once you said that we are just taking the best value of a and b, then anyhow we are getting the best relationship which is present between the features which we are
Correct.
Then if we are selecting the best relationship, then what the role lambda is playing after selecting the best relationship, then we are using lambda. So I'm not getting why.
No, when I'm choosing the best possible value of a and b,
That we have already done. Like minimizing error is we are selecting AB, best value of AB.
so that's what we are trying to talk about here. It is not always good to only minimize the error, because what happens, that's what I'm saying. See, once you are given 2 points, right? So if I choose a linear function, so this is giving 0 error, right? It passes through both. Exactly. This parabola also giving 0 error, and this function also giving 0 error. So which one to pick?
So is it possible like selecting a single value of E and P and you are getting 0 error with 3 different shapes, like with a straight line, with a parabola?
Correct. So in this setting, you may not get. You have more data points and you have less number of parameters to fit. But where you have more than here 60,000 parameters are there, and you have only 60,000 parameters are there, and you have only 1000 data points. So you can basically fit anything. So just like, see, line has how many parameters? 2 parameters, right? So the corresponding 2 points if I give, you can draw only one line, right? But if I want to fit a polynomial of, let's say, nth order, polynomial you understand, right? So you basically a function where you predict something like a coefficient is there, a1x plus a2x square plus a3x cube. You can take any power. So in that case, there will be many choices. So so passing through 2 points can be infinitely many possibilities, basically. So in that case, which one will you pick? So that will be the, and we'll see, generally we will be interested in this case. You will use the huge, feature vectors we will be using are really huge, and we will assume that there is a certain line in that space. See, linear model, the line is a very simple one. Do you think it will work in practice always? It may not be, right? You just consider the, so it may not work. So you want to, but still you want to use linear. And I explained to you how do you use linear. How do you use? You have, let's say, only x values, but then you generate x square, x cube, all powers, and in that you have a huge dimension, right? Each compound gives rise to one dimension. So you basically end up having so many parameters so that you can fit better. The idea is, given any data points, you have so many models. If the model has less number of parameters, your chances are also less that you will be able to fit this properly. Okay, but if you have more number of parameters, you have chances that you will fit properly, but then there are many choices. Which one to pick? Generally, it is this possible case we pick where we actually have belief that we will be able to fit the data more or less, as accurately as possible. But then there will be many possibilities. We don't know which one to pick. So that is the idea we are thinking. And Yeah, you are correct. If you have only two parameters, you will not have many solutions. So there is really no need of this one. That is correct. So generally, I am talking about this in general. So where you have large number of parameters. Basically, we will have large number of parameters if you consider the document classification problem. So there, the main setting that we take is it should have a prediction which is more or less accurate on the given examples, as well as the parameter values should be small enough so that there is not much variability. So in most of the machine learning problem in supervised learning will be having this kind of settings where you will fit some model with the data and you will try to fit it as best as possible with the constraint that model complexity should not be too much. This is called model complexity term. So that it determines that in future when you will be predicting, your predictions errors are also not too much. I'll just give one more examples on the classification setting. How do you classify? Let's say you are given news articles and you want to classify whether the articles are political in nature or they are talking about sports. So we have two categories. One is political and sports. I'll denote their output as positive and their output as negative. If the output is like +1, I say it is political. If output is -1, I say it is sports. Okay, so this is now given X. Okay, how do you predict? So basically, you have studied probability, right? So probability of Y given X. What is this quantity? What is the Y? Probability of Y given X. So it has two components, right? Y equal to 1 and Y can be -1, right? There are two choices. If either it is political or sports. So I will find the probability. What is the probability of being it political? That means what is the probability being it 1. So what will be the probability of being it -1 is just negative of it, right? 1 minus. So if this quantity is P, so this quantity will be 1 minus P, right? There is only two choices. So how will I classify? If I know one is more than the other. So if this quantity is more than 1. If I say that this article has a probability of 0.6 for being political. So obviously you choose that it is basically political because chances that it is sports is 0.4, which is less. So this is the idea, right? Which one is more? Now you take log of this. What do you get? This side will be 0, right? Log 1 is 0. So basically you want to compute this thing whether it is positive or negative. Now what we do is we again have the same earlier model. Let's say I'll choose it as some A0 plus A1 x1 or A2 x square, some model like this, which is basically again the A0 A1 are parameters dot product with 1x square, something like that. So basically I want to use same line setting here also, where the thing that I am predicting is this, and I will say if this quantity comes as positive, it is +1, or political, if it comes negative, then it will be sports, or Y is negative. Now same problem, how do you choose this A0, A1, all these coefficients so that you achieve your goal? And in this particular setting also, how we will be doing is, so I will call it in vector dimension. This is parameter vector A times feature vector X. So A transpose X. Okay. Now you take the log thing out. So probability of Y equal to 1 given X divided by 1 minus probability of Y equal to 1 given X is A transpose X, and this will be if you simplify, it will be probability of y equal to 1 given x will be 1 over 1 plus e power minus a transpose x. So given x, you will just have a dot product with the parameter vector and you will get this number between 0 and 1, which will give you a probability whether it is y equal to 1 is political. So you will get a probability. If it is less than 0.5, you will say it's sports. If it is more than 0.5, it will say, you will say political. Now how do you find that is the parameters? The same problem as your the earlier setting. How do you do? Because you will be given some articles x1, y1, where x1 will be either political or sports. So you will have many articles which are political, you will have many articles which are sports, and for articles which are political, y will be exactly 1. So this probability should be close to 1, and articles which are sports, it is not at all political. So y equal to 1, that probability should be close to 0. So you will again have that fit the data and some term which will say that A's are not too big, and you have some iterative algorithm to find those things. You will have the same thing as choosing lambda, and you find the best parameter by several trials of lambda. This classification setting is called logistic regression. You can read it off. And it's very useful for many classification problems, for document classification, from spam classification, anything. Any questions?
Sir,
Yeah.
you're saying that the values, you are tending to take values of parameters which are small.
Correct.
Let's say that we can fit two curves,
Uh.
and one has less number of parameters but the values are large, and the other one has a considerably more number of parameters but the values are small. Then what should be the choice?
There is always a trade-off. There is nothing like that this is best. So that's why I told a procedure called cross validation. You might first try with, let's say, linear, just the 2 parameter model. Let's say you try out linear model, 2 parameters, and you see you always use the n-10 training data for coming up with the best possible value, and you keep some data point on which you can test it and see how it is performing. So I told you for n number of data points, you know what are the corresponding outputs. So you will not be using all of n. You might use n-10 or n-1 and see and come up with the best possible A and B. Then whatever you didn't use, you test on that and see whether it is coming close to the one that was given to you. Now you see whether if the performance is good or bad. That's how we come up with. If the linear model doesn't work, then you go for the higher model, like the 1x squared, which is like quadratic model. If it doesn't solve, you go for higher. So this is called model selection problem, and there is nothing best than trying it out actually. But the idea is in large dimensions, because already number of parameters are large, linear things generally work well, and because the number of parameters are large, you have to use some sort of control so that your prediction accuracies are good enough. So whenever you are using some model, you always do this cross validation. Otherwise, you are not sure how you are going to perform on the unknown data. So this cross validation is always performed, and it's like recommended.
Can you suggest some more algorithms for like finding the relationship between features?
Between features?
Obviously, features means feature vector.
Huh. So what I didn't explore, I said you have good enough features. Generally, sometimes it might happen that the features are not good enough and it is not giving you good accuracy. Like if I have to classify news articles and I don't use the word model, I just use something else just the how many times some particular word appeared. I just might want to use some sports keyword. I just want to see whether those keywords are present or not. And same thing for political. And that is also a feature vector, right? I know these words appeared or not. And can you say based on this? So these different choice of feature vectors are there, and it is always left to the domain expert. So for that particular problem, he will be best to say which features are good for prediction.
No, actually not. I'm not asking about the features. I'm asking about the, like you have suggested 2 algorithm.
Sorry, I'll have to interrupt. So if there are any more questions, you have to take it offline. Present next speaker. Okay, so let's thank the speaker.